begin. So today you want to talk about some applications of integrals. How about just a few? Cover some new cool techniques on Friday, but now I want to talk about some of the ways that we can use integration. We already saw one. You're tracking motion, right? So if you're talking about position, velocity, acceleration, jerk. Etc. We understood that we move down this list by differentiating. And we can actually reverse this process by integration. And so there are problems that we can solve if we don't have the information going this way, but we have the information going that way. So we already saw that application. Another one that's closely related to this is called displacement. And that's pretty much if you have a reference position and you know some object is undergoing some sort of motion, maybe under the influence of some sort of force, and you can track its speed and so on and so forth. You can actually talk about the distance it has covered, either in total, which is called displacement, or, no, that's called total distance traveled, or with respect to some reference point. This is called displacement. This is distance traveled from some reference point. So example, let's say you have an object here and it traveled 5 meters that way, it turned around and traveled 4 meters back this way, right? Then we would say its displacement is actually 1 meter, right? The distance from the original reference position, it's 1, right? That's called displacement. While you'd say the total distance traveled would actually be 9 meters, right? If you just track how far this object has been traveling, in total, it is 9 meters. It traveled 5 meters in one direction, 4 meters in the other direction. But if you're measuring its distance from the original point, this reference point, it only moved 1 meter away after all was said and done, right? So that's the difference between displacement and the total distance traveled. Now, we can talk about both of these in terms of integration. So, conceptually, there's nothing else I have to tell you here. We pretty much developed integration using the motion idea as a motivating example, right? So that's where we kind of saw that, okay, velocity and position are kind of connected because the area under one is equal to the other. So all that still holds true. And ultimately, we can come up with these formulas. So, if V of t measures the velocity of an object, time t, then it turns out that we can talk about the displacement of the object. And this will simply be equal to, so this is displacement on, say, some interval AB. Okay, so this is from time equals A to time equals B. This is the initial time. T equals A to The displacement is simply going to be the integral, the definite integral of the velocity. So we saw that last time, and I described it in terms of distance traveled, but that was because it was always moving in one direction, according to our idea. But technically, to integrate velocity, you get what we call displacement. Now, in the event that you want to find the total distance traveled, now, the issue is, conceptually what we do is we think of, when it comes to velocity, direction actually matters. So a lot of times when you talk about some reference point, you will somehow make a distinction between the direction you're traveling from that reference point. So, for example, we might make the distinction that, okay, if we're moving to the right from the reference point, we'll consider this as positive velocity, and if we're moving to the left, we consider this in terms of negative velocity. And so what would happen if you're graphing the velocity function for this guy, for this part of the journey, the velocity function will be above the x-axis, or above the t-axis, the horizontal axis. But for this part of the journey, it will actually be below. So whatever distance is being covered there will be considered a negative distance covered, right? And so that's where you would get the positive magnitude, subtract the negative magnitude, will give you the displacement. But if you want, of course, want the total distance traveled, you'll actually want to take the negative part and make it positive. And how you can do that? Well, we know a function that does that, the absolute value. So that leads to the fact that we can say the total distance traveled on AB is simply going to be the definite integral of the absolute value of velocity. So here, it takes out the negative components when the object is moving in the negative direction. And so it considers everything positive, so all the area that we're considering is thought of as a positive area, and that will actually measure the total distance traveled. So we have these two formulas. So that's another application of integration. We can talk about displacement versus total distance traveled. Displacement is just the integral of velocity on the time interval being considered, whereas total distance is the absolute value. And that pretty much takes the directional component out of it. So there's no negative direction anymore. It just continues to measure the area and measure the total distance traveled. So let's do an example here. We did an example with the first application already. Particle's velocity at time t is given by, suppose we have this velocity function, t squared minus 6t plus 5. Find A, total distance traveled. Between time equals 0 and time equals 3. B, find the displacement of the object on the same interval. So tell me the total distance this object travels on that time interval, but tell me how far it actually moved from its original position on that same time interval. These are two different kinds of questions. For time values between 0 and 5, and the units can be whatever here. When is a particle moving forwards? backwards. What is the min velocity and the max velocity? So there is a word problem. A, total distance. This will simply be integral from 0 to 3 of the velocity function in absolute values. Which means we need to know where this guy's positive or negative, because this will be equal to v of t when v is positive. It will be equal to minus v of t when v is negative. So the first thing we have to do is figure out those two situations. How do you figure out when something is positive versus negative? Like if that's your goal, you have a function, you want to know when is it positive, when is it negative. How do you figure that out? What would your strategy be?
First derivative test.
Huh?
The first derivative test.
To figure out where it's positive versus negative? What does the first derivative test tell you about? Derivative doesn't tell you about position, it tells you about rate of change. So first derivative test will be if you're looking for when something's increasing, decreasing, where it hits a maximum or minimum. You don't look at that to tell where it's positive versus negative. Positive and negative are positions. When are you above the x-axis or below the x-axis? So you definitely want to look at the original function there.
You just plug in numbers.
Just randomly start guessing numbers
Well, no, use numbers that it gives you.
that give what?
Would you use the 3 and the 0 that it gives you?
Sure, but I want to know where does the function change between positive and negative on that interval? How do I figure out when it's above the x-axis or when it's below the x-axis, the t-axis? Like in general. Well, what does it mean to be positive and negative? When I say something is positive, what am I saying? What does it mean to be positive? Someone said, I don't know what that word means. What does positive mean? What does it mean for a number to be positive?
Zero.
Greater than 0. And negative means
Less than 0.
less than 0. So what's the common theme here? How do you judge?
Is it the x-axis?
Yeah, you pretty much find where it is 0. Figure out where it is 0, then you can figure out what side of 0 it's on afterwards. So you want to figure out what something is positive or negative, you set it equal to 0. So we're going to set this guy equal to 0. We want to solve that. That's going to be the first step. And so what is, how would we solve this equation? So this is for the intervals. So you set this equals 0. How do you solve this?
Factor it.
Does it factor?
Yeah.
What and what?
-5 and -1.
-5 and -1. So it hits 0 when t is 5. It also hits 0 when t is 1. So how do I know when it's positive or negative? Well, I'm going to plot on a number line 1 and 5, and then I'm going to test points. So if I were to plug in 0, for example, I would get a positive number. If I were to plug in, say, 2, this will be negative, that will be positive, I would get a negative number. If I were to plug in, say, 6, this will be positive, that would be positive, so I get a positive number. So that's how you'd actually test. Now for this one, we actually know, this is a parabola like that, right? So I already know if the x-intercepts are 1 and 5, I'll know where it's below or above the x-axis. But if it were an unfamiliar function, which would happen all the time, this is how you test. Figure out where it's 0, test the intervals by plugging in random numbers in each interval. So here I realize that v is positive, here and here it's negative here, which tells me on the interval 0, 3, our v is greater than 0 for, well, 0 to 1. And our v is less than 0 for 1 to 3. Which means the integral from 0 to 3 of the absolute value of v of t dt is going to be equal to, well, the integral from 0 to 1 of v of t dt minus, and I'm putting in that minus because of the definition of absolute value, 1 to 3 of v of t. That's going to be the total distance traveled. Don't forget the basics. You never know when they'll pop up. And so here we'd simply have 0 to 1 of this guy. Which this itself isn't hard to integrate. It's just a matter of the power rule. So this is t cubed over 3 minus 3t squared plus 5t. That's between 0 and 1. This guy's going to be exactly the same thing. So t cubed over 3 minus 3t squared plus 5t. This one's between 1 and 3. So here you would have, well, a third minus 3 plus 5 minus 0. Minus, over here, you would have 9 minus 27 plus 15 minus a third minus 3 plus 5. So what would we have here? Well, these guys are all going to be doubled because I have a minus of that expression, which is this. So this is 2/3 minus 6 plus 10 minus 9 plus 27 minus 15. And what's that? Well, minus 9 minus 6, that's minus 15. Minus 15, that's minus 30 plus 37, so that's 7. So we have 7 plus 2/3. 7 is 21 over 3, so this is 23 over 3. In whatever units. So that's the total distance traveled. If I want to find part B, displacement, well, that's just going to be the integral from 0 to 3 of the velocity function. So I don't care where it's positive or negative, I'm just going to do a straight computation of this guy. T squared minus 6t plus 5. T cubed over 3 minus 3t squared plus 5t between 0 and 3. So that's going to be 9 minus 27 plus 15. Now, the 9 plus 15, that would be 24 minus 27, so minus 3. And what does that mean? The object ends up 3 units behind where it started. So that kind of means the situation was like the object moves forwards and then it moves back 3 units behind where it started. So this distance here is minus 3 because it's 3 units behind it. But if you were to measure the total length that it traveled, it's 23. So 7 2/3 of a unit. Which means you can also figure out that this part must be like this whole length here is 7 2/3. So you subtract 3 from there, you get this. Then you can half that distance to get this distance. So that's one application, displacement. You can talk about the total distance something moved versus the distance it moved when you're thinking of its original position as a reference point. Here is another application. So one was motion, 2 was displacement. So this is the third application. Average value is a pretty important one. So you might recall what it means to actually do an average in the basic statistics sense, right? But I give you a list of 10 numbers and I ask you to find the mean average of these 10 numbers. You would add up these numbers and you would divide by the total number of numbers, which would be 10. Now, when you're doing statistics and probability, eventually you get to a point where you have to consider things called continuous probability distributions. This means that you're in a situation where your probability is given by continuous functions. So you can't just add up a finite number of numbers, but you have some function that you want to talk about its average value over some interval. Okay? But there's an infinite number of values there. How do you find the average in that case? Well, so you might recall the mean average of, say, x1, x2, x3 to xn is given by x1 plus x2 plus blah, 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 plus xn all over n. Well, what if we have an uncountable number of values? Which surprisingly shows up pretty early. You take a basic probability course here and you'll cover this before the end of the semester. Uncountable, by the way, is a technical term. It actually has a very specific meaning in mathematics. But it just means an infinity that's bigger than the infinity of the integers. So there's an infinite number of integers, but it turns out that there are infinities that are less, that are bigger than that infinity. Okay, so you want to count something like that. You have that many values, an infinite number of values, and you want to find their average in an analogous way to this guy. So one thing you can recall that we looked at not so long ago is on AB. Let's say all our values fall into this interval. We have, we can imagine that these numbers are lined up on the interval. Right, so here's like your x1 and your x2, blah, 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 all the way to your xn. And we can find the delta x by b minus a over n. In other words, I can think of my n as b minus a over delta x. Now, we want the average value of some function f of x on the interval AB. Okay, so here's our function doing its thing on this interval. For each x number I can plug in here, it'll give me some output. If I collect all these outputs, right, which there will be an infinite number of them, and I want to find the average of all those outputs. Well, basically, the average is going to look like, well, I'm going to add up all these outputs. And I'm going to divide it by the number of outputs there are, which is n. However, in the case here, I know that my n is actually b minus a divided by delta x. So this is the average of n values. In other words, I can look at the average value of a function as f of x1 plus da da da, f of xn, all of that times delta x divided by b minus a, which is going to be some number. Now if I want to find the average value of an infinite number of values, I simply take the limit and let n go to infinity. So this is actually equal to, we have a shorthand for this. This is the summation of f of xi times delta x. This is all over b minus a. This is I goes from 1 up to n. And to find the average of all values, well, this is just going to be the limit as n approaches infinity of this guy. Now, the bottom is a constant, it's just b minus a, so that can come out. And we're left over with the limit as n approaches infinity of the summation of this, which by definition is the Riemann sum that defines the integral. So in practical terms, we kind of mentioned this, the main goal, one of the main collateral benefits we get from defining the derivative was linear approximation. So we set out talking about speed, but there's a lot of use in thinking of the derivative in terms of linear approximation. And in the same way, a collateral damage of being able to find area is being able to add up a lot of things in a very sophisticated manner. You can think of an integral as a really sophisticated adding algorithm, right? So if you want to add up an infinite number of things, a lot of times there's going to be an integral hidden in there somewhere. And so that pops up. These are the kind of places where calculus will pop up a lot. So in statistics, it will pop up even somewhere like here, and Yeah, once you start talking about continuous probability distributions, probability and statistics goes the way of calculus and multivariable calculus and all that stuff, and that's where it starts to get interesting. Okay, so this is actually a formula that we know. So now we can get the average value of a function on an interval, right? So you think of all the outputs of a function on a certain interval, and you want to find their average is given by one over b minus a times the integral from a to b of r to x. It's another application. You want to find the mean average of an infinite number of things that you can describe in terms of a function. That's how you would do it. Of course, provided you can actually integrate this guy. Provided f is integrable. That's a third application of integration. Let's find the mean of an infinite number of values. Well, integration is how you would do something like that. Do I have an example? Oh, I mentioned something here. I didn't remember I wanted to mention this. There's also a mean value theorem for integrals. So let f be continuous on AB, then there exists C in AB such that f of C will equal to the average value, which is defined. Very similar to the mean value theorem for derivatives, but we have one for integrals as well. So if you take the average of all the values that a function is outputting, there has to be some value in the interval that actually is the average output. Because if all values were below the average output, the average would be lower. If all values were above the average output, the average would be higher. Right? There has to be some value that's at the average output. Now let's go to an example. Consider this function, not very complicated, x squared on the interval 0, 2. A. Find the average value of f on 0, 2. B. I think this is actually included. This is probably included. Okay. So again, we have y equals x squared. We only care about 0 to 2, but notice that your function is outputting an infinite number of values. Every coordinate here is filled in with some number. So if I were to take all those values, add them all up, and divide by infinity, the number of values there are, what would the result be? A, the average value is simply going to be 1 over 2 minus 0 times integral from 0 to 2 of x squared dx. If I were to add up all possible outputs between 0 and 2, and then find their mean average, that would be the result. So of course we know that this is x cubed over 3 between 0 and 2. So this gives us 8 over 6. I can take 2 into both of those. Turns out the average value would be 4/3. So add up all these y values here, pick every point and look at the y value. Pretty much every point here is going to give us some value. Add up the values of these green dots, divided by the number of green dots, and 4/3 will be your answer. Of course, there's an infinite number of such dots. So we know here that the minimum value outputted by our function is 0, and the maximum value outputted by our function is 4, but there are numbers that the outputs are all in between those ranges. Now if I were to add up all these numbers and find their mean, 4/3 would be the answer. And for B, we want C in 0, 2 such that f of c equals the average value. This would mean that I want c squared to be equal to 4/3. This would mean that my c would be equal to technically plus or minus, but we'll ignore the minus. So this will be 2 over radical 3. And here we take the positive value. So if I take the point, whatever it is, 2 over radical 3, and I plot that across, that output is actually going to give me 4/3. So for this particular value, it's going to give me 4/3. And that's the average value of these functions. Yeah, you guys, I'm pretty sure you actually will cover that in a class at some point. Like if you're a science major, you might be wondering, where would we encounter a situation where I need to find the average of an infinite number of things? You'll encounter it at some point. Even if you're a bio major, you'll encounter this at some point. So you really don't have to go far in mathematics to encounter situations like this, where you want to find an average of an infinite number of things. So integration will actually pop up in that case. One other application. So that was how many applications? We did motion, displacement, average value, motion, displacement's average value. Yeah, we did 3. Okay, so here's the 4th application. Where did I start here? Area between curves. Now, ultimately, this idea would be the full, this includes the full solution to the area problem. You might recall when we were looking at the area problem, we actually relaxed the conditions a lot just to get our calculus to work. So there was this blob that we wanted to find the area of. I wanted to throw this on the x, y axis. However, it would not pass the vertical line test, so it's not a function, and I can't talk about all the things you know about functions here. So what we did was we looked at, okay, let's just look at half of it, you know, and let's find the area of that, right? So that gave us the idea if we want to find the area under a curve, which we sliced up and put rectangles on that and used Riemann sums to figure out the area of that, and that gave rise to the integral. Now, what happened to the other piece, right? So it turns out, well, we could have done the same for the bottom half of the curve, right? Set up our Riemann sums and use an integral to find that. So in total, the area of this object is really the area between the green curve and the red curve. This is the solution to the area problem, right? That's how we would fit it all together, right? So now, to finish the solution to the area problem, we need to know, well, how would I find the area between two things? We know how to find the area under something, but what does it mean to find the area between two curves? That brings us to this application. So now suppose that our f of x is greater than to g of x on some interval a b. So here's a, here's b, here's my f of x doing this thing, and here's my g of x doing its thing. So this is f of x, and this is g of x. Okay, so now we want the area between these two curves. What is a? Well, it turns out we can use our knowledge of integration to figure out a by considering one curve at a time. What we can do is notice that if I want to find this guy, I could actually think of it in this particular way. So here's A, here's B, here's A, here's B, here's A, here's B, and this is my F, bottom is my G. Okay, so to find the area that I care about, which is this guy, it's A, I can think of it as the following. Find the area under the F function. So I'm going to be finding this green area. The area under F, well, by definition, that is AB, f of x, dx. And then what I'm going to do is I'm going to find the area under the G function. And you realize if I take this area and subtract that area, I'm left over with the area in the middle. So pretty much I'm going to minus the area under G. So I can actually find the area between two curves by finding the area under the larger one and subtracting the area under the smaller one. Our area is going to be the integral of a to b of f of x dx minus the integral from a to b of g of x dx. By the properties of integrals, we know that integrals distribute across sums, so this is just f of x minus g of x dx. And in general, I can say that the area between the two curves is going to be equal to, here's how you want to think about it, top function minus the bottom function. Figure out who's on top, figure out who's on the bottom, subtract them, and integrate. dx. to the area between functions. No, doesn't seem like a very mathematical formula, not the usual notation, but there comes a point which you'll see it in Calc 2, but it'll definitely become a factor in Calc 3. Sometimes you have to ditch the elegant way of writing things down for a more intuitive way of writing things down, and location is going to be important, top, bottom, right versus left, all that sort of thing. It's going to be good if you start thinking in terms of positions as well. You know, start getting your spatial awareness skills in check. Because multivariable calculus is going to kill you otherwise. So I think a nice way to really conceptualize this idea, how do I find the area between two curves, is to just know this. Integrate the top one minus the bottom one. And you really want to know, and you really should start being able to think in that way in general, I would say. So if someone were to ask you, how do you know where something is positive versus negative? You should know, well, let's say equal to 0 and then test the integrals. Make sure your language, you can actually talk about mathematical formula in terms of everyday language. That's an important thing. So I'd actually rather you memorize it like this, as opposed to memorizing it with F and G, which could mean whatever. So that's the last application. You want to find the area between two curves, that's how you do it. Let's do some examples. I should have a few here. I guess we'll finish them up next time. Conceptual one, try to explain your idea, maybe write down a formula for how you would actually do this. So pretty much you're looking for this area here. Say I told you this was at A, this was at B, this was at C. And hopefully start with the integration.